Here is what I'll do about electromagnetic waves. Okay. Really, to start from Maxwell's equations and it will be possible for just a little bit, and if you learned a little bit more of math, like let's say you're going to know in a year, it would be possible for you, for all of us, to start from Maxwell's equations and derive what we know as the wave equation. So we can actually do this Maxwell's amazing calculation of the speed of light. However, right now if I actually go through that calculation, you don't know what wave equation is, you don't know some of the tricks that are needed to get from Maxwell's equations to the wave equations. So I think it will be a loss of good lecture hours. Right. Instead, I'll try to motivate what electromagnetic fields, what the solutions look like. Okay, these self-supporting solutions, one of which is visible light we have. So, first, let me tell you what do electromagnetic waves look like. First of all, there is a direction of propagation, so they are propagating waves. They go along some direction, right? So, let's talk about now. I'll just write an electromagnetic wave which is propagating along the z direction. Okay, electric field of x, y, z, and t will be very simple. It will be the maximum value of the electric field. Let's say that it's along x direction. And then I'll have cosine kz minus omega t. First thing we should notice here is these are called plane waves. What does that mean? This is a wave propagating along z. So this is the propagation direction. And if I look at so let's say this is the z-axis. If I take planes perpendicular to that, on this plane, the value of the electric field is the same on all points of the plane. So basically, if this is my propagation direction, you should think of planes perpendicular to this propagation direction, and the value of the electric field and magnetic field on these planes are going to be the same. All right? So that's what's called a plane wave. So you basically, everything happens on these planes. So I don't actually, and if it's propagating along z, this is the x direction and this is the y direction, right? Maybe I should be more careful. Let's say this is the x direction and this is the y direction. Okay. So I don't actually have to plot the value of the electric field as a function of x and y. It doesn't change as a function of x and y. Okay. how is the behavior along z, or propagation direction? Well, as a function of z, here is let me rewrite it. The x component of the electric field is E0 cosine kz minus omega t. That depends on which time I'm plotting my function. Okay. Let me put t equals to 0 first. When t equals to 0, what happens? E is, at time t equals to 0, Ex is just E0 cosine kz. That's a usual cosine we know of. It's not very hard. So let me plot Ez. That's at time t equals to 0. It's going to be a nice cosine. What happens if I plot it a little bit later? Oh. What happens if I plot time not at exactly 0, but if I plot it, let's say 0.1 times 2 pi over omega. Why do I choose 2 pi over omega? Because I know this is some sort of period. Right. Now, if let me do it in another color. Let me do that in. That's going too fast. What was I doing? I'm plotting the same electromagnetic wave, the plane wave electric field at 0.1 2 pi over omega. So what's my function now? Ex is E0 cosine kz minus, it was omega t, so omega times 2 pi times 0.1. Omegas cancelled. Hey, this is just the same cosine shifted a little bit by a phase, isn't it? So basically, it's the same cosine a moment later, which is shifted by a phase. If I do the calculation, same calculation, if I plot the wave at 0.22 pi over omega, what would I see? I'll see that it's shifted a little bit more to the right. Right. Or in general, this is what we see. We're seeing propagation along the direction of propagation. Okay, so my whole wave together is shifting along the z direction. Let's try to figure out what's the velocity of this shift. Okay, so we call it speed of light, but here's what I'll do. I'll write Ex is E0 cosine omega k x minus kz minus omega t. Or I'm going to write this as follows. It's always a cosine of k some z. So it's as if my z is shifting with time. Okay, so this is like the origin. I'm shifting the origin of my coordinates. You can think of that, right? Instead of the wave shifting, maybe I'm shifting the coordinate system. And what's the velocity of the shift? The velocity of the shift apparently is just omega over k. Okay? Or in other words, these two constants I defined, omega and k, must be related. This has to be the speed of light. My frequency is C times K. What is K though? If I go back, this was just cosine KZ. So what's the distance between two peaks of my electric field? K times Z must be 2 pi, right? So the distance between two peaks, which I am going to call the wavelength, must be 2 pi divided by K. Okay. In other words, so lambda is 2 pi divided by K. In other words, omega is C times 2 pi over lambda. Or maybe you remember this relation in another way. Instead of omega, which is the angular frequency, I'm going to define nu, which is called the frequency. So I'll write it 2 pi nu is 2 pi C over lambda. 2 pi is cancelled. C is equal to lambda times nu. Speed of light is wavelength times frequency of the oscillations. Okay. Okay. So far, what did I talk about? I said there's a definite direction of propagation, and electric field and magnetic field values are constant on these planes, perpendicular to it. And I've said the wavelength, so basically the length of one oscillation of the wave, is 2 pi over K, and that is connected to the speed of light through this nice formula. C is lambda times V. I said nothing about the magnetic field or the direction of the electric field here. And here comes our third rule about the directions. E and B are perpendicular to each other. They are also perpendicular to the direction of propagation. So, in other words, if I'm looking at this light bulb, there is an electromagnetic wave coming from that light bulb towards me, towards my eye. What's the direction of propagation? It's coming from the light bulb to me, so this is the direction of propagation. The electric field and magnetic fields are not coming towards my eye or going away from it. They are perpendicular to this direction of propagation. Okay. So there is also one more important thing. It turns out the direction of E cross the direction of B is equal to direction of propagation K. Right? So if I actually want to plot these fields, let's say this is the direction of propagation Z here. This is my x-axis and this is my y-axis. What does the electromagnetic wave, the fields look like? It's exactly what I drawn. Electric field will be along the x-axis. It will be a cosine which is shifting with time. And it turns out the magnetic field is in the other axis. It will be in the y-axis. And which brings me to my fourth property of the electromagnetic waves. E and B are in phase. So when electric field is maximum, so is the magnetic field. When they are minimum, they are both minimum. Okay? But at each point, E cross B gives me the direction of propagation. Okay? Now, whenever your field is perpendicular to the direction of propagation, these are called transverse waves. Okay? Transverse means oscillation or whatever is happening is perpendicular to the propagation direction. There is another kind of waves which are called longitudinal waves, where the motion is happening in the direction of propagation. For example, our sound waves, when sound comes from my mouth to your ears, what happens is that the direction of propagation has air molecules moving in the same axis, basically. Okay? Electromagnetic field is happening in the transverse axis, sound is happening in the longitudinal axis. In most generally, waves can be a mixture of both. For example, another kind of wave which is terrifying is earthquake waves. Okay? So earthquake waves have both longitudinal character and transverse character. And it turns out the longitudinal earthquake waves actually travel faster than transverse waves. What happens is that, okay, so if you actually, let's say an earthquake happened, I first will feel shaking in some direction, like this, okay? Then I can immediately tell one thing. I can say the center of the earthquake, because longitudinal waves came first, must be on the axis I was oscillating. Okay? After a while, and it turns out these waves are actually weaker and they are not very destructive. After a while, what will happen is that the transverse waves will arrive. So I will actually start oscillating perpendicular to that direction. And if those are strong, I'm not in a very good place. I should start running out, okay? But I was amazed to learn that in ancient China, people where a lot of earthquakes happen, they had this simple mechanism. They had a ball with what looks like ping pong balls made out of marble on it. And when an earthquake happened, they fell. If there's oscillation, these marbles fell into the ball. And by just looking at which marbles fell first, they could guess the direction of the earthquake, and they immediately sent riders, people on horses in that direction to see where the earthquake happened. So electromagnetic waves are good, right? That's we can use to communicate. It's better than riders. Now, so what else are our properties? Let's talk about the properties of these electromagnetic waves. We said, hey, so let's write the full detailed solution. An electromagnetic wave propagating along Z would be E is in the let's say x direction, I cosine kz minus omega t, and B will be in the y direction with the same time dependence. Okay. Now, here is the thing. How is the strength of electric field and magnetic field related to each other? Let's try to figure that out. Okay. Now, first of all, why is the magnetic field generated, and what's generating the magnetic field here? Let's think about that. Is there a current somewhere? No. The only thing that may be generating the magnetic field is the time rate of change of electric flux. Right? That was displacement current. Similarly, what's generating the electric field? It must be the induction due to the change of magnetic field. So, here is what I will do. Let me try to plot these things. So this is my y-axis, this is my x-axis, and this is my z-axis. Keep in mind that everything is constant on planes perpendicular to z. Right? Now, which way is the electric field? Electric field is in the x direction. So, if I take let me do it. A loop like this. Which is perpendicular to the y-axis. So a loop in the xz plane. What will be d phi b dt through this loop? That's what I need. D phi b dt through this loop will be proportional to b0 because b is in the y direction, right? It will depend on how thick of a loop I get, but that'll still be going to be proportional to b0. How about, and what was my Faraday's law? Faraday's law told me that E dot dl, the induced electric field, is basically minus d phi b dt. So this is going to be proportional to b0. Now, how about this is going to generate an electric field? Now, let me do the reverse. Let me take a loop in the yz axis. And on that, I'm going to write integral b dot dl, which is going to be, there is no current anywhere, b dot dl is just mu 0 epsilon 0 d phi e dt. And this d phi e dt must be proportional to E0. Right? That's the strength of my electric field there. So, all in all, what do I see? If I have E0, I must multiply it by mu 0 epsilon 0 to find b dot dl. But if I have b0, I'm actually not multiplying it with anything. So basically, what should be the ratio of E0 over B0? I'm doing this twice, B0 to E0, E0 to B. E0 over B0 square must be just inverse of that, right? 1 over mu 0 epsilon 0, or E0 must be 1 over square root of mu 0 epsilon 0 B0. And E0, what's 1 over square root of mu 0 epsilon 0? It's the speed of light. That was the amazing thing. E0 must be C times B0. Wow! Now you may say, electric field is C times B0. C is 310 to the 8. So electric field is super important. Maybe let's not care about magnetic field at all. But that's a very terrible comparison. These have different units, electric field and magnetic field. It would be really like comparing apples and oranges, right? I always wanted to say that in a physics 102 course. So, okay. Now, let's compare something that we can actually, that has the same units. So let's look at the energy stored in the electric field and the energy stored in the magnetic field. All right? What was the energy stored in an electric field? Do you remember the energy density of an electric field? 1 over 2 epsilon 0 E squared. The energy stored in magnetic field was 1 over 2 mu 0 B squared. So let's compare these. Let's compare, if this is E0, this is B0. This is going to be 1 over 2 mu 0 E0 divided by C square. But C square is 1 over mu 0 epsilon 0. So mu 0 is cancelled. 1 over 2 epsilon 0 E0 squared. Hey! In the electromagnetic wave, UE is equal to UB. So, if I have energy carried in an electromagnetic wave, it's being carried equally by the electric field as well as the magnetic field. Now, let's be very careful here. Do you remember how we defined electric field? We said, hey, I don't want to use Coulomb's law all the time. Let me invent this thing as a mathematical convenience, and it's going to be easier to use that. But after a while, we said, hey, this thing can store energy. And now we're saying something even more important. We're saying not only can it store energy without the need of any charges or currents nearby, it can actually carry energy from one point in space to the other point. So energy can be carried by electromagnetic waves. Furthermore, we will see in our next lectures that momentum can also be carried. So it's kind of disconcerting. I mean, when I go out into the sun, there's a nice, well, not today, but over the weekend there was nice sunshine, right? I go out and I'm not surprised at all that I'm being heated up. You know, I go out into the sun. It's very natural to think that I'm actually heating up. Why? Because energy of the sun, what happened in nuclear reaction inside the sun, is being carried by this electromagnetic wave, which is being absorbed by me. That's fine. What's really interesting is that sun is also pushing me a little bit. Okay. Really, and it's when you will see how to calculate this amount of that push, it's much smaller compared to our own scales. But when the electromagnetic field strength, when there is a lot of light around, that's a very important force. Now there are some proposals for sailing to the outer solar system using this light force. Okay, so you're going to need a very large sail, but sunlight hitting you will propel you enough. Maybe take a object quite fast to the outer reaches, to Pluto, to Neptune. Okay. Even more interestingly, just a few weeks ago, a bunch of scientists and some futurists, they said, hey, you know what we can do? We can get a very powerful laser and put small devices, a few kilograms of devices on a very large scale, and we can blast them with that laser so much that they can reach to almost, 1/3, 1/5 of the speed of light. So within 10 to 20 years, they can reach the next star to Alpha Centauri. Okay. And they'll not do only one, they'll do hundreds of them, so some might veer, of course, but some of them will reach that star, and they'll shoot pictures and send back to us the pictures. So I think that's a very bold proposal, which I don't see happening in my own lifetime, but nonetheless, it's nice. So momentum carried by light is very important. It may become very important. Actually, it's also already very important. It's very interesting if you take a course in astrophysics and you ask the following question. Why does the sun not cave in? Gravitationally, sun is not a solid object, right? It's a plasma. So, gravitationally, if I'm at some point on the sun, all gravity is pulling me in. So why does the sun not get smaller and smaller? There must be a force that's pushing out. You may say, hey, maybe it's it's a plasma, so there may be some sort of charge pushing out. It's a neutral plasma. That's not the case. It turns out it's just photon pressure. It's just electromagnetic waves. And actually, if at some point, it's a very precarious balance, if there aren't enough photons around, if the push is not enough, the sun collapses. The star collapses, it becomes a supernova, the collapse generates some other mechanisms inside, and then it explodes. That's called a supernova explosion. Thankfully, our sun is not going to become a supernova. It's not going to do anything bad for the next 5 or 10 billion years. Okay, so we should be safe. Right. But energy created and transported by the sun has become more and more important over the last 10 years. And maybe within the next 10 years, solar energy will be cheaper to generate compared to our current mechanism of generating electricity. How do we generate electricity? We burn something. That's, like we burn coal, we burn natural gas, maybe we do some nuclear energy. There is also hydro, but it's actually surprisingly small percent of the total world's generation. Turkey has a lot of hydroelectricity. Norway has a lot of, apparently, hydroelectricity. And many nations do not have any viable water sources for hydroelectricity. That's interesting. So everyone seems to have coal. It's easy to burn. So that's how we generate. But someone actually calculated if India was using as much electricity per person as the United States, then almost all of the world will be 5 times more polluted by the outcome of carbon. Okay. If you add in China at the same levels, if you add in all the world at the same level as Canada and the United States is using energy, then the world is running out of resources. Okay, we're going to be too polluted. We'll be like Beijing in winter, right? We will not be able to breathe. So solar energy is a very clean way of generating electricity, but until the last 5 years, people could not generate enough electricity. Well, okay, you could do it in the lab, but it cost too much to generate a battery, solar battery, which is going to power anything significant. Right now, really, renewable energy is starting to take over. And maybe within our lifetime, we may not be seeing devices going to Alpha Centauri, but I think we may see solar power taking over all our infrastructure. It's quite possible. The new electric cars are running on DC. So we are doing something wrong. We are generating AC and converting it to DC again. Almost everything in our homes can be run on DC without any problems. And if we can generate DC locally, instead of getting, right now the energy we are using is probably generated at, I don't know, Keban Dam in 1,000 kilometers away, and it's being carried here with a lot of loss on the wires. Why not just put some solar panels onto the roof and generate our own electricity here? We need very efficient solar panels. If you calculate how much of the sun's energy we are actually converting into our use, it's a very, very small fraction. All worlds, if we have solar panels covering something like a small nation, I don't know, Andorra, that would be enough for the whole world's energy needs. So we don't have to, cover half of the planet with solar cells to generate electricity. So I think within your lifetime, within the next 20 to 30 years, you will see a lot more about solar energy, about the energy carried by electromagnetic waves. So I'll tell you one more thing. I keep talking about light all the time, but electromagnetic waves are actually a part of the spectrum. Okay, so what we said is, okay, I'll do something like this. I'll say, let's talk about wavelength lambda. Do you know what's the wavelength of the light we can see? Okay, it turns out it's 500 to 900 nanometers. The light at 500 nanometers is a deep purple. The light at around 900 nanometers is a red. So all different colors we perceive. Color perception is a very complicated topic, but it's generally related to wavelength. Okay? Now, so this is the visible spectrum. What happens if I use light or electromagnetic wave with a larger wavelength? For example, around 1500 nanometers. This region has a name. This is the red. So this is the infrared. Okay? Why did I actually mark 1500 nanometers? It's because all the fiber optic cables carry light exactly at that frequency. Okay, it's infrared. There's also one more important thing. The sun's peak power is around this. So it's the infrared which heats you up when you go out into the sun. Okay? What happens if I go to, well, not 1500 nanometers, so this is nanometers, so this is 1.5 micrometers. If I go to 10 micrometers, well, okay, this region of the electromagnetic waves are very crowded because of thermal effects. Okay, but these are called the terahertz region. It's becoming more powerful, more important. What happens if I actually move a little bit further? If I actually move to, say, 1 millimeter. When was the last time you went to an airport? I mean, there are new devices, especially in the United States and somewhere in Europe. You go in and they actually rotate around you, right? These are called millimeter wave detectors, okay? So what they do is, And also the device where we work in, the bomb detectors, okay? So those are millimeter, they work at the millimeter range. So it's not millimeter wave detectors. Some radars for detecting planes also work close to that range. What happens if you go to 1 centimeter, around 1 centimeter range? You know, there are some devices which most of you use, which use radiation at 1 centimeter. No. Microwave ovens, your microwave ovens are 1 centimeter, maybe 3 centimeters, okay? So this is called the microwaves. How about if I go to 10 centimeters or 1 meter, let's say? This is where your radio waves are, okay? And in between somewhere around 10 centimeters is a device you use too much. What's that device? No, come on. The hair dryer doesn't communicate with, I don't know, I mean, maybe you do communicate with your hair dryer, but it's just, you don't need it. No, not much of it, right? Your cellular phones, your GSM standard is around 10 centimeters, okay? Now, here's another question. Why do you think, Maxwell wrote his equations within 40 years, 30 years, Hertz have shown the existence of electromagnetic waves. Why didn't people have cellular phones right away? Why did it take a century to get to cellular phones? They are using the same principle. Sorry? There was no computer engineering, but I'm not thinking about playing games on the cellular phones. I'm thinking of the old Nokia, okay? But you actually have some valid point there. The problem was that they could get to radio, 1 meter waves, okay? Now what happens with these 1 meter waves? Their wavelength is very large, which means their frequency is small. So they could create currents at that frequency. Okay. They could not, however, create currents which are faster, oscillating faster. So they could not create wavelengths smaller than that. So what happened with the semiconductor industry is that we could get faster and faster LC circuits. We could get faster and faster oscillators. Your computers have chips which are running at 4 gigahertz. What's that? It's the frequency. It can actually switch that fast. Okay? And then, when you're at gigahertz, you can create electromagnetic waves around a few centimeters, maybe 5 centimeters. And that's how your cellular phones work. If you can efficiently oscillate at a certain frequency, you can efficiently generate electromagnetic waves at that frequency. And it turns out this is actually a good, because we can talk on these phones because we know how to oscillate something at around gigahertz. How about larger waves? Radio, TV is somewhere here. Do you know what's the longest wavelength electromagnetic wave we use for communication? It's around 100 meters. Sorry? No, actually, it turns out satellites, we use pretty much microwaves. Okay, so satellites are not big things. Okay, they have a big, maybe antenna, but the receiver is small, so I mean, think of your Digiturk antenna, right? I mean, it's the whole antenna, the collector is large, but the receiver there is not very large, so it must be collecting more or less at that centimeter range. It turns out submarines, when you're in salty water, you need big wavelength to communicate. So submarines use all of their body, and sometimes maybe they even trail some wire to communicate with each other and the world. Okay, so they use around 100 meters, maybe 200 meter wavelength electromagnetic waves. But that's pretty much the limit we use for communication. It gets very slow to communicate with those waves. Now, here's the thing. What happens if I go further and further in wavelength? It turns out there is not much useful there. Okay, there are some waves at that point. We cannot efficiently generate them. We do not care about them. They do not carry much energy. So let's do the other thing. Let's go over the last 5 minutes to the other side. I was thinking about the visible spectrum. So this was purple. So what's the other side called? Yes, so it's not called purple. This is called violet. Okay, so this is the UV region. Ultraviolet. Now I said the peak of sun's energy is coming in the infrared. But what if you go into if you tan under the sun? What changes the color of your skin is not infrared, it's the ultraviolet. So if you go to a tanning station, which I certainly advise against, if you tan yourself, what they do is they blast you with UV. They give you a lot of UV radiation. How about if I actually go a little bit further than that? Well, there are things called, extreme UV, which is somewhat important for creating chips. But the wavelength is probably around 1 nanometer here. What if I push further and further? If I push a little bit further, I actually get to X-rays, where it's more or less 1 angstrom wavelength. And X-rays, now they start to become dangerous. Okay, X-rays, they are used heavily in medical industry, yes, but they also start to be dangerous because we are not talking about quantum mechanics, but it turns out the shorter the wavelength of any radiation, the more energetic its energy units, its photons are. So what happens with X-rays, if you get too much of X-ray, it can knock around in your cells. Especially, it can change your DNA. It can knock something out of the DNA. DNA repairs itself with a lot of mechanisms, but if it does not, that's not good news, right? If I actually even push further, if I go sub-angstrom, exactly, if I go to femtometers, then I get gamma rays. And these are definitely bad for us. Okay, I mean, there is no, if you want to get cancer, that's the way to do it, right? You go and shine yourself, shine some gamma rays to yourself. The thing is, we cannot, how do we generate gamma rays? That's it, we need a bomb, right? So or we have a naturally radioactive compound, but gamma rays are still used in medicine. Do you know how they are used? There is something called gamma ray surgery. They take a lot of very small radioactive gamma sources and they focus gamma beams. And how do they focus gamma beams? They basically get the heaviest possible element, lead. They make gamma rays pass through almost everything except lead. So they make 1 meter of lead, small holes through it, and radioactive source on the other side. Many small holes, all arranged in some hemisphere. And there is a region here where a lot of gamma rays come. And if you can make the tumor in that region, if you can put your tumor into that region, it kills the tumor. But you have to be very careful. It basically kills anything that's going into that region. Okay. Nonetheless, it's actually quite amazing. People can do that. So there is this whole range, and we have learned to utilize almost all of these electromagnetic waves. Our technology, what has changed since 1880s? people living in London in 1880s, that was the most advanced city there. They had horses that are pulling their carriages. They had to actually burn oil for light. Once we learned electricity and magnetism and this whole electromagnetic spectrum, that's what our technology, the 20th century, 21st century, is based on electromagnetism. All of our developments have happened through these equations, Maxwell's equations. On Wednesday and next week, I'll do two things. I will actually solve some examples related to electromagnetic waves and look at how they carry momentum, and then I'll do an overall review for the final. I'll see you on Wednesday.